Hey there everybody, Mr. D here, and in this video we're going to recap how we can graph a rational function with a removable discontinuity. So let's go ahead and take a look at our step-by-step. If you need to pause the video to jot any of this down or read any of this, feel free. The step-by-step process, we always factor first. Anytime you have a rational function, you always want to factor first. Then we're going to find the domain. Remember, the domain is all values for x in which we don't have any funky business happening, meaning there is no zeros in the bottom of a fraction. Now we're going to simplify if possible. Now you'll notice that this is in green, and that's because if anything cancels, you get what is called a removable discontinuity. And what I mean by that is if we had a function, I'm just making this up, say x plus 3 times x minus 2, and then x plus 1 times x minus 2, you'll notice that we have domain restrictions where x is not allowed to be negative 1, x is not allowed to be negative 2, or sorry, positive 2. However, these factors would cancel each other out. And if they canceled out, well, now that value for x that wasn't allowed of 2 is completely good to go here in the simplified, but not from the original. So what we just did is we took one of those discontinuities at 2, a point in which our function wasn't continuous, and we removed it by canceling. Hence, removable discontinuity. Once we find the removable discontinuity, we'll then go through our process as we've done before to get all the other pieces of information. So I've got a few examples that are already kind of written out for us, and then we'll do one from scratch, and that'll be the duration of this video. If you want to skip ahead, feel free. If you want to speed it up, feel free. All right, so the vertical asymptote, x-intercept, y-intercept, that's all from the previous lesson, previous video. Go back, check that out if you need. Removable discontinuity. This is the new stuff. So removable discontinuities occur at the divided out factors. I'm going to say, and this isn't as mathematically accurate, the canceled out factors. Now, once you cancel those out, you can plug that x value back into the simplified version of that function to find the y coordinate. Now, when we graph a removable discontinuity, it's going to look like a little hole in the graph that just got plucked out. All right, so let's see some examples here. Oh, reminder on the horizontal asymptote there. All right, so first example, we have x plus 4 over x minus 2, x plus 4. In the bottom, x is not allowed to equal 2, not allowed to equal negative 4. But then I'm noticing that, hey, these x plus 4s would actually cancel each other out. So I'm going to have a removable discontinuity showing up. So when all is said and done, I've got domain restrictions at 2 and at negative 4. Those show up in the domain here. These domain restrictions are either going to be vertical asymptotes or holes in the graph, removable discontinuities. And then the simplified form, after we've canceled things out, is just 1 over x minus 2. So in this original function, I was not allowed to plug in negative 4. However, in the simplified function, I can plug in negative 4 all day. This would be 1 over negative 4 minus 2, which is negative 6. So 1 over negative 6, negative 1/6. So the only thing new here is the presence of factors that could cancel out. Everything else we've already seen. All right, so now let's figure out what all this means. We have a vertical asymptote at 2. Some of you might want to say, but what about that negative 4? Negative 4 is in the domain. That's not going to be a removable, that's not going to be a vertical asymptote. Since that got canceled, that's going to be a removable discontinuity. So we have a removable discontinuity at negative 4. And to figure out the y value, we're going to plug in negative 4 for x to that simplified function. I couldn't plug it into the original one because I'd get 0 over 0, but I can plug it into that simplified format. So I have removable discontinuity at negative 4 comma negative 1/6. Let's see another one here. Similar process. It's already factored x over x times x minus 3. I've got domain restrictions at 0 and at 3, so you see those in my domain here, 0 and 3. But then the x's will cancel out. Those are both free-floating plain old x's. So if I simplify that, after those things have been canceled, I get 1 over x minus 3. So these domain restrictions of 0 and 3 are either vertical asymptotes or removable discontinuities, holes in the graph. Well, since that x minus 3 stays after the simplification, that's going to be a vertical asymptote. Since the x's canceled away, they were removed. Those represent my removable discontinuity. Now, to figure out the y value for that removable discontinuity, the hole in the graph, we just plug in 0 for our simplified. It has to be simplified. Can't do the original. Has to be the simplified form. Plug in 0 and see what we get. So 1 over 0 minus 3, we get negative 1/3. All right. One more, and then we're going to graph this one from scratch. Oh, yeah. All right, this one, it's not factored for us, so always factor first. Factor out the numerator, x minus 2 and x plus 1. That denominator, we've got a difference of squares pattern. Difference of squares factors down into conjugate pairs, so x minus 2, x plus 2. We look at the denominator. That's going to tell me my domain restrictions. 2 and negative 2 are off limits. 2 and negative 2 cannot be included in the domain, so those are represented here in my domain intervals. These domain restrictions, 2 and negative 2, are either going to be vertical asymptotes or removable discontinuities. Well, I'm noticing here that x minus 2's cancel out. They've been removed. Since those cancel out, they tell me where a removable discontinuity occurs. So x minus 2 as a factor corresponds to an x value of 2. The x plus 2 did not cancel out, so that stays as a vertical asymptote. Now, if I really wanted to, I could find the x-intercept here by plugging it in, or setting that top part equal to 0, but it's not asking for it, so I won't. Our removable discontinuity is 2 comma something. To figure out that something, we're going to plug in 2 for x. So 2 plus 1 over 2 plus 2, we get 3 over 4. All right. Now let's see one from scratch. We're going to get all this information, then we're going to graph it. If you need to pause the video to jot down this example, feel free to do so. If you want to speed it up, if I talk too slow, that's cool too. All right, always, always, always factor first. Up top, I've got conjugate pairs. Conjugate pairs factors to difference of squares. Down below, numbers that multiply to a negative 12 add up to a positive 1. That would be a x plus 4 and x minus 3. At this point, I'm noticing my domain by looking at the bottom here. X is not allowed to equal negative 4, and x is not allowed to equal 3. So my domain is going to be negative infinity to negative 4 to 3, and 3 to infinity. Make sure you always write these in order, lowest to highest, least to greatest. All right. Let's see if anything cancels. Oh, would you look at that? The x minus 3's cancel. The x minus 3's cancel, and that value that corresponds with it was a 3. So I'm going to have a removable discontinuity at 3 comma something. My remaining function is x plus 3 over x plus 4 after that cancellation has occurred. If I want to figure out that y value, I can plug in 3 to this function. I couldn't have done it over here because I'd get 0 over 0. But after we've removed those factors, now we can. Let's see, 3 over 3, that is 6. Sorry, 3 plus 3, 6. And then 3 plus 4 is 7. This would be 6/7. That does not reduce. Cool, I've got my removable discontinuity. Now we can also get our vertical asymptote. I'm still left with this x plus 4. So I have a vertical asymptote at x equals negative 4. Lo and behold, the numbers that show up in my domain restrictions also happen to be vertical asymptotes or removable. Interesting. Let's go on to, let's do horizontal asymptote since it's right there. We look at the degrees, x squared over x squared. It's a tie. We have 2 over 2 there. So now I take the ratio of coefficients. That would be y equals 1 over 1. Well, that's just 1. So y equals 1, which then tells me my end behavior as well. So I can get that going. 1 and 1. Let's get our x-intercept. X-intercept joining the party. We look at the numerator. What value for x would make that numerator equal to 0? Well, that would be -3. We can get our y-intercept by plugging in 0 for x. Let's see, that would be 0 plus 3 over 0 plus 4. That's 3/4. So 0, 3/4. Holy smokes, we are burning through this. And then range. So range is when we go bottom to top. Now we have a few things breaking up our range. We have a horizontal asymptote. That's going to break up our range. We also have this y value from the removable discontinuity that breaks up our range. So what I'm actually going to do is I'm going to graph this first just to get a visual, but we're going to have negative infinity to 6/7, 6/7 to 1, and then 1 to infinity. I'm going to wait to write that down until we see what this thing looks like. All right, let's get to graphing here. Vertical asymptote at x equals -4, so we go to x equals -4, 1, 2, 3, 4, and we get our asymptote dotted line. Then we have a horizontal asymptote at +1. So we're going to get a dotted line going at +1. We have removable discontinuity at 3,6/7. 3,6/7. Well, that would be, let's see, 6/7 is just shy of 1. So 3 and then almost 1 would be right about there. X-intercept at -3. So we have an x-intercept at -3, which is right there. A y-intercept at 3/4. So 3/4, 0.75. That's going to be a little bit lower than that RD value. So we'll say like, now let me use a different color here. Say right about there. It'll be 3/4. And that's about it. Okay. So if we graph this, it's going to be a rational function, so we're approaching our asymptotes values. As we get closer, we mirror and mimic those asymptote behaviors. So this is what my graph is going to look like. Should be arrows on the ends of those two. All right, so now here's what I was saying with the range. The range, we go bottom to top. There's clearly a break here at the asymptote. However, there's also a break right here. So if we're trying to do the vertical motion, there's a little tiny skip right at 6/7. So right as we approach that hole, there's a little discontinuity there. And then we have this little region between the hole and the horizontal asymptote. So the way we would write that is going bottom to top. We went from -infinity all the way up to 6/7, and then between 6/7 and 1, and then from 1 to infinity. Again, these values of 6/7 come from the y value of the removable, and the 1 come from the horizontal asymptote. All right, that is that for that lesson. You guys know the drill. If you have any questions, let me know. And as always, folks, good luck, have fun, be safe, roll tide.